Welcome to Night Watch Observer. It's lovely to have you here tonight. Before we begin, let me ask you the question I always like to ask. Where in the world are you watching from? What time is it in your corner of the night? Maybe you're tucked under a heavy blanket with the rain coming down somewhere outside. Maybe you're on a train or a couch or a bed in a room where you've left one small lamp glowing in the corner. Wherever you are, whatever the hour, I'm glad you found your way here. Settle in. There's no rush at all, and if you enjoy these slow journeys into the dark, a quiet like and subscribe really does help this sleepy little channel keep going. Small creators like me genuinely rely on your support to keep the lights low and the stories coming. So if you'd like more nights like this one, that little tap means more than you know. And to those of you who have already subscribed and come back night after night, thank you, truly. You're the reason the Night Watch keeps its post. Now I should warn you, as I always do, I'll try my best not to make tonight so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely about the dark before you drifted off. A fair trade, I think, and if your eyes do grow heavy partway through, if you slip under before we reach the end, that's perfectly fine. The story will still be here. The stars aren't going anywhere. You don't need to follow every word, and you certainly don't need to understand every number I say. Let them wash over you like the sound of distant water. We'll go slowly, one small mystery at a time. So, let's begin, shall we? I want you to picture something for me gently, the way you'd picture a place in a dream rather than something you're trying to memorize. Picture the sun, our sun, warm and golden and familiar. The one that lights your mornings and sets behind your buildings or your hills in the evening. Now picture moving away from it, not a little, not even a lot. Picture moving so far away that the sun shrinks from a great burning disk to a small, bright star, just one bright point among the others, barely warmer looking than the rest. Picture going so far that if you held up your hand to where the sun is, you could very nearly cover it with the tip of one finger. That is where something of ours is right now tonight, as you lie there listening to my voice. There is a spacecraft out there. Its name is New Horizons, and as of the middle of this decade, it sits roughly 60 times farther from the sun than the Earth does. 60 times. Let me give you a single number to hold on to, and then I'll let it go, and you can let it go too. Astronomers measure these distances in something called an astronomical unit, which is just a tidy way of saying the distance from the Earth to the sun, about 150 million kilometers. One astronomical unit, one trip from us to the sun. New Horizons is around 60 of those out, 60 Earth-to-Sun distances stacked end-to-end into the dark. That comes to something on the order of 8.5, nearly 9 billion kilometers from home. 8.9 billion kilometers. Say it slowly to yourself. It's a number so large it stops meaning anything, and that's all right, because the feeling underneath it is what matters. The feeling is distance. The feeling is aloneness. The feeling is a tiny machine, smaller than a grand piano, drifting in a darkness so complete that the sun itself has become just another star. And it isn't sitting still out there. It's moving. New Horizons is racing outward, away from everything it has ever known, at something like 13 or 14 kilometers every single second. That's roughly 3 of those astronomical units every year. Every year it pushes 3 more Earth-to-Sun distances deeper into the night, and it will keep doing that faithfully, quietly, for as long as it lasts. It is leaving. It has been leaving since the day it was born, and it is never coming back. Here is the gentle, astonishing thing I want you to know. The thing that makes this little machine worth a whole night's story. Out there, in that perfect, dark, 8.9 billion kilometers from your warm bed, New Horizons still has one working eye. It still carries a camera, a sensitive optical telescope camera, with a name that sounds like it belongs to a friendly old machine, which it rather does. It's called LORRI. The letters stand for the Long-Range Reconnaissance Imager, but you don't need to remember that. Just think of it as the one eye still open in the deepest dark any of our machines have ever reached. And right now, tonight, that eye is doing something almost unimaginably bold for such a small, distant, fragile thing. It is measuring the brightness of the entire universe. I'll say that again because it deserves to be said slowly. Out there in the dark, that little camera is being used to measure the total, summed-up glow of every galaxy that has ever existed. All of them. Every star in every galaxy across all of cosmic history added together into one faint, almost impossibly faint glow. And it points its eye at the dark and it counts that glow. And here's where I have to plant a small seed in your mind, a little open question that I'm going to ask you to carry with you, half asleep or not, until much later in the night. When they pointed that eye at the dark and measured it carefully, the dark came back about twice as bright as it should have been, twice as bright as all the known galaxies in the universe added together could account for. There was a glow out there that shouldn't have been there. A faint, extra light, real and measured that nobody could fully explain. Hold that for me. Twice as bright as it should be. We'll come back to it. We'll come back to it more than once, because the story of what that means is the story of tonight. And it does not have the tidy ending you might expect. But for now, just let it sit there in the back of your mind, like a lamp left on in another room. The dark came back too bright, and we'll find out, slowly, together, what that might mean. Now, why the dark? Why does a spacecraft have to go 8.9 billion kilometers out into the black just to measure how bright the universe is? Couldn't we just do that from here, from a nice telescope on a mountaintop, or from one of our space telescopes orbiting comfortably close to home? And the answer to that beautifully is no, we can't. And the reason why is the whole reason this story exists at all. So let me walk you through it gently, because it's one of those things that seems strange at first and then becomes perfectly, peacefully obvious. Think about the last time you were somewhere truly dark, maybe out in the countryside, far from any town on a clear, moonless night. You looked up and you thought, now this is dark. And it was. Compared to a city, sky washed orange by streetlights, it was magnificently dark. But here's the quiet truth. Even there, even on the darkest, clearest night you have ever stood under, the sky around you is not actually empty of light. It's softly, faintly aglow, and that glow, gentle as it is more than bright enough to drown out the thing New Horizons is trying to see. There are, it turns out, 3 great curtains of light hanging between you and the true dark of the universe. 3 foreground glows, all of them local, all of them ours, all of them gently in the way. And I'd like to introduce you to each of them one at a time, like guests at a very quiet party. The first is the one closest to home. It's called airglow. Even on the clearest night, the thin upper layers of our own atmosphere are very faintly luminous. The air itself glows softly, a chemical shimmer high above your head, where sunlight has stirred the molecules during the day and they release that energy back at night. You almost never notice it, but a sensitive instrument notices it everywhere. The atmosphere we breathe and live under is ever so slightly a lamp. And so any telescope sitting beneath the air, any telescope on the ground, is trying to see the faintest light in the universe through a pane of softly glowing glass. So we go above the atmosphere. We send a telescope up into orbit above the airglow. Surely that solves it. And it helps, but now the second curtain is waiting, and this one is patient and enormous, and it follows us everywhere we go inside the inner solar system. It's called the zodiacal light, And the cause of it is something you might not expect. Our solar system, the space between the planets, isn't truly empty. It's gently dusty, scattered all through the inner system between us and the Sun and out past Mars. There is a vast, thin haze of tiny dust grains, the ground-down crumbs of ancient comets and shattered asteroids, drifting in their billions and trillions through the sunlight. And sunlight, falling on all that interplanetary dust, scatters off it the way a beam of light catches the floating motes in a sunlit room and makes the whole shaft of air seem to glow. That scattered sunlight is the zodiacal light from certain dark places on Earth just before dawn or just after dusk. You can actually see it with your own eyes, a faint pyramid of pale light leaning up from the horizon along the path the planets follow. It's beautiful.
And it is absolutely everywhere in the inner solar system, a soft, glowing fog of sunlit dust that no telescope near Earth can ever escape, because the telescope is sitting right inside the fog.
This is the big one. This zodiacal glow, this sunlight bouncing off interplanetary dust, is so much brighter than the faint signal we're hunting that trying to measure the universe's true background from anywhere near Earth is a little like trying to measure the light of a single distant candle while standing inside a softly lit room. The room isn't bright, but it's far, far brighter than the candle. And so the candle is hopeless. You simply cannot see it from in here. And then there's the third curtain, gentler than the others, but still there. It's the scattered light of the stars themselves and of our own galaxy. Starlight from all across the Milky Way, bouncing and diffusing through the thin clouds of dust that lace our own galactic neighborhood, smearing a faint glow across the sky. We'll come back to that one much later tonight, because it turns out to matter more to our story than anyone first realized. But for now, just add it to the count. 3 curtains. Airglow from our own air. Zodiacal light from our own dust. And scattered starlight from our own galaxy. 3 soft glowing veils, all of them local, all of them ours, all of them standing squarely between us and the faint, true light of the deep universe beyond. Now, here is the lovely, simple, almost obvious solution that New Horizons gives us. You can't pull those curtains aside, you can't switch off the airglow or sweep away the dust or dim our own galaxy, but you can do one thing. You can leave. You can travel so far out, past the planets, past the great fog of inner system dust, out into the clean, cold dark beyond, that 2 of those 3 curtains simply fall away behind you. Go far enough, and the air is long gone, of course. There's no atmosphere out there to glow. And go far enough past the orbits of all the planets and out into the outer reaches, and the interplanetary dust thins out and fades behind you too. You leave the fog. You step out of the softly lit room and into the corridor, and at last, for the first time, you can see the candle. That is exactly what New Horizons has done. It has gone farther from the dust than any working camera ever has. It sits right now in the cleanest, deepest, most genuine darkness that any human instrument has ever recorded. Not the darkness of a country sky, not the darkness of orbit, the real dark, the dark beyond the dust. And it is the only place we have ever reached where you can even attempt to measure the true faint light of the universe itself, because it's the only place where our own local glow has finally, mercifully, gotten out of the way. There is something almost tender about that if you let yourself feel it. To see the faintest light in all of creation, you don't build a brighter instrument, you don't strain harder, you simply go somewhere dark enough and quiet enough and far enough away that there's nothing left to drown it out. You go out into the deep, and you wait, and you let your eyes adjust to a darkness no one has ever stood in before. There's a lesson in that somewhere, I think, for nights like this one. But I'll let you find it on your own. So, we have our little spacecraft 8.9 billion kilometers out, racing away at 3 astronomical units a year, the only working eye in the deepest dark we've ever reached. And we know why it's out there, in that perfect black, past all 3 curtains of our own local light. Now let me tell you gently what exactly it's trying to see. What is this faint glow it's hunting? What is this light of the whole universe? It has a name. It's called the Cosmic Optical Background. And I'll explain it slowly because it's one of the most quietly beautiful ideas in all of science, and you don't need any background at all to feel the wonder of it. Think of every star that has ever shined, not just the stars you can see tonight, not just the stars in our galaxy, every star in every galaxy across the entire history of the universe, the first stars that ever ignited in the young cosmos, billions of years ago, the countless suns that have lived and died since, the galaxies so far away that their light has been traveling toward us for almost the whole age of time. Every one of them poured out light, and much of that light is still traveling, still crossing the dark, still arriving faintly from every direction at once. Now imagine you could add it all up. Every photon of visible light from every star in every galaxy that has ever existed, all of it summed together into one single, faint, smooth glow filling the whole sky. That sum, that grand total of all the starlight the universe has ever made, is the cosmic optical background, the optical background, the light. It is, in the most literal sense, a glowing record of everything that has ever shined. I find that almost unbearably lovely, and I hope you do too, drifting there in your warm, dark room. Out beyond all the dust, the sky isn't truly black. It carries the faintest possible whisper of light, and that whisper is the combined glow of every fire that has ever been lit in the cosmos. To measure it is to take, in a way, an audit of all the starlight ever made.
A single number that holds within it every sun that has ever burned. Now you may have heard somewhere of a different cosmic background, a more famous one. It's called the Cosmic Microwave Background, and the two are gentle cousins. So let me set them side by side for just a moment, because together they bracket the whole story of the universe, and the contrast is beautiful.
The cosmic microwave background is the universe's very first light. It comes from a time about 380,000 years after the Big Bang, when the whole cosmos had cooled just enough to become clear, to let light travel freely for the very first time. That ancient first light is still around us, everywhere, stretched and cooled by the long expansion of the universe until it's no longer visible light at all, but a faint microwave hum, a leftover warmth from the dawn of everything. That's the microwave background, the first light, the afterglow of the beginning itself. And the cosmic optical background, the one New Horizons is hunting, is its companion at the other end of the story. It isn't the light of the beginning, it's the light of everything that came after. It's the sum of all the light that structure made, all the light produced by stars and galaxies once they finally formed and began to shine. The microwave background is the universe's first breath. The optical background is everything the universe has done with its life since. One is the spark, the other is the whole long fire. Two background glows then, two faint signals soaking the entire sky from every direction. The first light, in microwaves, the afterglow of the Big Bang, and the summed light, in the visible, the glow of every star and galaxy that has ever lived. Together they bracket cosmic history from end to end. And our little spacecraft, 8.9 billion kilometers from home, sitting in the cleanest dark we've ever found, is out there right now trying to measure the second one, trying to add up all the light the universe has ever made and hold that grand total in a single, faint number. And remember the seed I planted, the lamp I left on in the other room? When they finally measured that faint glow, that summed light of all creation, out in the perfect dark where nothing local could drown it out, the dark came back too bright. Brighter than all the galaxies we know of, added together, could explain. About twice as bright. A faint extra glow, real and measured and stubborn, that simply shouldn't have been there. And so the question, the gentle, enormous, still open question that we are going to wander toward slowly over the rest of this night, is this: why? Where is that extra light coming from? Is our count of the galaxies somehow incomplete, missing whole crowds of faint and distant ones too dim to see one by one? Or is something stranger going on, something out there in the dark we don't yet understand at all? Is the universe, in some real and measurable sense, simply too bright? No need to reach for the answer now. We have all night, and the answer, when we get to it, is not a tidy one. It bends and turns and doubles back on itself in a way that's far more honest and far more interesting than any neat ending could be. For now, just rest with the question. A small machine alone in the deepest dark, measuring all the light there is, and finding more of it than anyone could explain. So let me set the scene a little more fully before we go any further, because to understand what New Horizons is doing right now, in this dark, it helps to know how it got here and what it has already done along the way. This little spacecraft has lived an extraordinary life. It has visited worlds. It has flown past the most distant things we'd ever reached. And only now, in this last long chapter, has it become something its makers barely dreamed of when they first sent it on its way. Let your breathing slow. Let the weight settle out of your shoulders. We have a long, gentle road ahead of us tonight, all the way out to 8.9 billion kilometers and the strange, too bright dark at the end of it. And we'll take it slowly, the way we always do, one quiet mystery at a time, Welcome to Night Watch Observer. It's good to have you here with us in this quiet stretch of the night, wherever you happen to be. Maybe you're under a heavy blanket with the lamp still glowing soft in the corner. Maybe you're on a train, watching the dark slide past the window. Maybe it's very late and the rest of the house has long since gone still. Wherever you are, and whatever time it is in your corner of the world, I'd love to know. Tell me down below where you're listening from tonight. It's one of my favorite things, imagining all of you scattered across the dark side of the earth, all of us awake together for a little while. And if you find these slow journeys help you drift off, a quiet like and a subscribe really do help this small channel keep going. Small creators like me rely on your support more than you'd think, and every one of you who stays means a great deal. To those of you already here, already subscribed, already part of the Night Watch, thank you, truly. Now settle in and let's go. So, let's begin where the spacecraft actually is. Not where it was, not where it's going, but where it sits at this very moment, while you lie here listening. Right now, as you breathe, there is a machine about the size of a grand piano drifting through a darkness so complete it's hard to picture. It is roughly 60 times farther from the Sun than the Earth is. 60 astronomical units in the language astronomers use, where 1 astronomical unit is the distance from the Earth to the Sun, about 149.5 million kilometers. Multiply that out and New Horizons is somewhere around 8.9 billion kilometers from home, from you, from the warm bed you're lying in. And it isn't sitting still, it's racing. Every single second, it travels another 13 or 14 kilometers outward, away, never to return. In the time it takes the Sun to make one full circuit of our sky, New Horizons moves about 3 astronomical units farther out. 3 more Earth-to-Sun distances every year forever. It is leaving the solar system and it is never coming back. And it does this quietly, without drama, the way a slow river finds the sea. Out there, the light is almost gone. At 60 astronomical units, the Sun is just another very bright star, and its warmth, its glow, is more than 3,600 times fainter than the sunlight that touches your skin on a summer afternoon. Think of that. A whole dazzling daytime dimmed 3,500 times over until it's barely more than a strong ember in an enormous black room. That is the world New Horizons lives in now, a cold, faint, endless dark. And in that dark, it is still seeing. That's the part I want you to hold on to, because beyond all the planets, beyond Neptune, beyond the icy worlds of the Kuiper Belt, there is exactly one working sensitive camera, just one. It sits aboard New Horizons and it has a name, LORRI. The Long-Range Reconnaissance Imager. A small telescope, really, built to take crisp pictures of distant worlds as the spacecraft swept past them. And it still works. It still opens its single eye in the dark and lets the faint light fall in. There were others out there once, of course. The Voyagers, the Pioneers. 4 spacecraft that left the solar system before New Horizons did, and 2 of them, the Voyagers, are even farther out. Voyager 1 well past 160 astronomical units now, but their cameras went dark long ago, switched off decades back to save what little power remained. They sail on, blind. New Horizons is the lone seeing eye in the deep dark, the only one left out there that can still look up and look out and measure. So that's the scene. A small, fast machine, nearly 9 billion kilometers from home, alone, half-blind worlds behind it, with a single working camera and a slowly fading heartbeat of power. And it is doing something nobody expected of it when it launched. It is measuring the brightness of the whole universe. And here is the thing I promised you. The thing we'll wander toward all night. When it measured the darkness out there, the cleanest, deepest darkness any human instrument has ever sat in, the darkness came back wrong. It came back about twice as bright as it should be. Twice as bright as everything we know how to account for. Just rest with that for a moment. The darkest place we've ever reached, and it's glowing more than it has any right to. Now, why does the darkness matter so much here? Why send a camera nearly 9 billion kilometers from home just to look at nothing? Because that nothing is the whole point. From where you are, here on Earth, or anywhere near it, you cannot truly see the dark. Not the real dark. The sky around us is contaminated, washed out by light we can't easily switch off. For one thing, there is zodiacal light. That's sunlight scattered off countless tiny grains of interplanetary dust drifting through the inner solar system, a faint, broad glow that smears itself across the heavens. There is scattered starlight, the light of stars bouncing around where we don't want it. And here on Earth, there's airglow, a soft, ghostly shimmer the upper atmosphere makes all on its own, all night long, even with every city light put out. 3 veils, 3 sources of brightness, all of them drowning out the faint signal anyone would want to measure. You can't subtract your way out of all that, not cleanly. The only real cure is distance, to leave the dust behind, to climb up and out, past the planets, past the grains of zodiacal dust that the sun lights up, into a place where those veils simply fall away. And that is exactly where New Horizons is. It sits in the cleanest dark any camera has ever recorded, the darkest sky ever measured by any instrument we've ever built. Not because the universe got darker out there, but because at last we got far enough away from our own light to actually look. And what is it looking for in all that perfect black? It's looking for something with a name that sounds grander the longer you sit with it. The the Cosmic Optical Background, the COBE. Let me unfold what that actually is, slowly, because it's one of the most quietly staggering ideas in all of astronomy. Every star that has ever burned, in every galaxy that has ever formed, across the entire history of the universe, has poured out light. And that light, a great deal of it, is still traveling, still crossing the dark. The cosmic optical background is, very simply, the sum of all of it, the combined, faint, mingled glow of every galaxy that has ever existed, added together into one soft wash of light, filling the whole sky in every direction. It is, in a sense, the accumulated shine of everything that has ever shined. Picture it like this. Imagine you could gather every candle ever lit in the history of the world, every fire, every lamp, every match, and blend their light into a single, faint, even glow spread across a vast room. You couldn't point to any one flame. They'd all have melted together into one quiet brightness. The cosmic optical background is that, but for stars, for galaxies, for the entire universe, across all of time. And it has a famous older sibling, one you may have heard of, that helps make sense of it, the cosmic microwave background, the CMB. That one is the universe's very first light. It comes from a moment about 380,000 years after the Big Bang, when the cosmos had finally cooled enough for light to travel freely for the first time. That ancient first glow is still around us, everywhere, stretched and cooled now into faint microwaves. It is the oldest light there is. So think of the two of them as a pair, bracketing all of cosmic history. The cosmic microwave background is the universe's first light, the afterglow of its very beginning, and the cosmic optical background is everything that came after, all the light that stars and galaxies have made in the long ages since. The CMB is the opening note, the COB is the whole song that followed. Two background glows, two quiet whispers filling the sky, telling us about two very different chapters of the same enormous story. And out there in the dark, with its one small working eye, New Horizons set out to listen to that second whisper, to measure the song of all the galaxies, to take, in a way, an audit of every star that ever was. Let your breath slow again. We're going to keep drifting outward, gently, toward how that audit was actually done, and what it found, and why the answer still won't sit still. But there's no rush. The little machine has been out there for years. The light has been traveling for longer than that. It will all still be here, waiting when we get to it. But before we get to the measurement and the anomaly hiding inside the darkness, we should take a moment to understand how New Horizons arrived at this particular place in the story. Because the mission didn't begin as a cosmic background observatory. It began as something much more pointed and specific and personal than that. It began with Pluto. And to appreciate what the spacecraft is doing right now out in the deepest dark it has ever reached, you need to know what it was built to do first, and what it found, and why those two earlier chapters closed so beautifully before this third, stranger chapter opened. So let's go back, way back, January 19, 2006. That was the day New Horizons left Earth, and the manner of its leaving is worth pausing on for a moment, because it tells you something about the ambition and the urgency behind the mission. It launched from Cape Canaveral on a cold winter morning, riding an Atlas V rocket, and it left at a speed that no spacecraft built by human hands had ever matched at launch. Roughly 16.26 kilometers per second relative to Earth. That's about 58,500 kilometers per hour, if you prefer a bigger number. And most people find the bigger number more satisfying. 58,500 kilometers per hour is almost impossible to hold in your head as a real thing. So here's a smaller measure. From the moment it left Earth, New Horizons reached the distance of the Moon in about 9 hours. The Moon, which is roughly 384,000 kilometers away, 9 hours, a long day's work in human terms. A journey that took Apollo astronauts nearly 3 days. New Horizons did it before the next day's breakfast. And then it kept going. It didn't stop at the Moon, of course. It swept past Jupiter in February 2007, using that giant planet's gravity as a slingshot, gaining another 4 kilometers per second and shaving years off the trip to Pluto. It crossed the orbit of Saturn without stopping, crossed Uranus, crossed Neptune. It was in the dark for almost a decade, running on stored sequences, barely sipping power, much of the team's equipment sleeping to preserve energy for the work still to come. 9.5 years after launch, it arrived. July 14th, 2015. Mark that date gently somewhere in your memory, because it matters. New Horizons passed within about 12,500 kilometers of Pluto's surface. To give you a sense of scale, that's a little closer than a transatlantic flight between New York and London. The spacecraft was screaming past at 14 kilometers per second, so it couldn't slow down and orbit. There was no second pass, no lingering. It had one chance, one narrow window of minutes when it would be close enough to see Pluto clearly, and it used every second of it. And what it saw. Nobody had ever seen Pluto as a real place before. For all of human history, even with the best telescopes, Pluto had been a point of light, a dim pixel, a mathematical certainty wrapped in mystery. And then on July 14, 2015, it became a world. The first image that came back clearly, the one that took days to download because of the slow trickle of data across billions of kilometers, showed something that stopped people cold. There was a vast, bright, pale plane in the shape of a heart, enormous, smooth, impossibly clean. The nitrogen ice plane was later given the formal name Sputnik Planitia, but the whole feature, that soft, light-colored heart shape splashed across the face of Pluto, was named Tombaugh Regio, in honor of Clyde Tombaugh, the man who had first seen this world as a moving dot in a blink comparator way back in 1930 when he was 24 years old and working long nights at the Lowell Observatory in Flagstaff, Arizona. We'll come back to Clyde Tombaugh later in this night. He has a very particular relationship with this spacecraft, one that is worth holding in reserve for a little while. Let it rest there, just at the edge of your awareness. The mountains on Pluto's surface were made of water ice. Water ice. Out there, at billions of kilometers from the sun, water is rock. It's the bedrock, the solid stuff out of which mountains are built, because water ice is harder than anything made of nitrogen or methane at those temperatures. The nitrogen is the soft stuff, the stuff that flows and settles into smooth plains. And standing up from those plains were mountain ranges made of water, solid and ancient and cold. New Horizons saw all of it in that one brief, irreplaceable pass. It saw the atmosphere above Pluto, a thin blue haze. It saw evidence of glacial flow, nitrogen ice moving slowly across the surface, the way water ice moves in glaciers on Earth, only vastly, unimaginably more slowly. It saw the dark, reddish patches in the south, coloring that comes from complex carbon chemistry baked by radiation over billions of years. Pluto turned out to be a world, a complicated, layered, geologically active world with real weather in its own strange, cold, nitrogen and methane way. And then, 9 hours after closest approach, New Horizons passed out the other side of the Pluto system and kept going. That was the first chapter. It closed beautifully. The second chapter opened on New Year's Day 2019. The team had used the Hubble Space Telescope to search for another Kuiper Belt object within New Horizons' reach after Pluto. They needed something close enough to the spacecraft's trajectory that it wouldn't use up all the remaining fuel to get there, but far enough away and small enough to be genuinely different from everything we'd seen before. They found one. It had been given the catalogue designation 2014 MU69, and before it was formally named, the team nicknamed it Ultima Thule, after the ancient term for the farthest known edge of the world, a poetic choice. The place beyond the last known place. It was officially named Arrokoth eventually, an Algonquian word meaning sky. January 1st, 2019, New Year's Day. New Horizons flew past Arrokoth at a distance of about 6.6 billion kilometers from the Sun, 6.6 billion kilometers. And Arrokoth, when it finally came into focus in the images that trickled back over the following weeks and months, turned out to be one of the strangest, most pristine things we'd ever seen. It was a contact binary. Two distinct lobes, each roughly shaped like a flattened disc or a rounded pancake, gently stuck together at their centers like the two halves of a snowman. Not a snowman that had been rolled and pressed into shape, but two separate objects, two primordial clumps of rock and ice that had formed separately in the very early solar system, drifted together very, very slowly over millions of years, and settled into each other so gently that neither broke. They just held. And there they stayed, locked together for 4.5 billion years out in the cold darkness of the Kuiper Belt, largely undisturbed. When scientists looked at Arrokoth, they weren't just seeing a small Kuiper Belt object. They were seeing, essentially, the original moment of planet formation, a frozen fossil. The very first step in the process by which dust grains become pebbles, pebbles become boulders, boulders become these gentle, slow-moving clumps, and clumps eventually become planets. Arrokoth showed that the step from cloud of rubble to proto-object probably happened very quietly, very slowly, two pieces drifting together softly rather than smashing together violently. The whole story of how planets form might be written in Arrokoth's unhurried, pancake shape. And then New Horizons passed that too and kept going. 2 chapters closed. Pluto, a world that turned out to be far stranger and more alive-looking than almost anyone had expected. Arrokoth, a time capsule from the very first page of the solar system's story. 2 things that no human eye or instrument had ever seen clearly, now seen, studied, understood. And still, the spacecraft flew on. This is the part of the New Horizons story that most coverage never reaches. Most articles, most documentaries, most breathless recaps stop at Pluto's heart, maybe glance at Arrokoth's snowman shape, and close. Mission accomplished. Journey over. A heroic arc with a satisfying ending. But that framing misses the most interesting part. Because New Horizons didn't stop, it's not drifting silently with its instruments switched off, just coasting into the endless dark. It's doing science. Right now. Tonight, while you're listening to this, in your bed or on your couch or wherever it is you've settled in, New Horizons is out there roughly 60 times farther from the Sun than Earth, and it is using its one working eye to try to measure something far bigger than Pluto. The eye has a name. LORRI. The Long-Range Reconnaissance Imager. LORRI was designed with one purpose: to take detailed, sharp pictures of things very far away in the solar system. Its mirror is about 20 centimeters across. It was built to read the texture of Pluto's surface from hundreds of thousands of kilometers away, to resolve craters and mountains and frost deposits. It's a telescope, yes, but a very specific kind, a high-resolution black and white imager, tuned for distance reconnaissance in a place where the Sun is already much dimmer than at Earth. Nobody, when they were designing LORRI in the early 2000s, was thinking about the cosmic optical background. Nobody was planning to use it to measure the summed light of the entire universe. And yet, that is exactly what it's now being used for. a planetary close-up camera built to squint at surface features from far away, repurposed to weigh the light of all the galaxies that have ever existed. There's something quietly wonderful about that. About the way that the best tools, the honest ones, the ones that were built to do one hard thing well, sometimes turn out to be capable of completely different hard things that nobody anticipated. LORRI sees faint things clearly from very far away in very dark conditions. Those happen to be exactly the qualities you need if you want to measure the faintest background glow in the universe. It's not magic. It's not an accident. It's physics applied faithfully to a problem its designers never imagined. But here's where it gets more interesting and a little stranger. Because using LORRI to measure the cosmic optical background isn't as simple as pointing it at the sky and reading a number. It's more delicate than that, much more delicate. And the difficulty of the measurement is central to why the results turned out to be so contested, so surprising, and so stubbornly unresolved. Here's the basic method. You point LORRI at a patch of sky that is, as far as you can tell, completely empty. Not at a bright star, not at a galaxy, not at anything interesting. You pick the dullest, darkest, most featureless patch you can find, well away from the bright band of the Milky Way, well away from any nearby bright object that might scatter light into the camera. And you take a long exposure. The image that comes back is not completely black. It has a faint, diffuse glow. And that glow is what you're trying to understand. But here's the problem. That glow contains many things at once, and most of them are not the cosmic optical background. Most of them are nuisances, interlopers, light from things much closer and more mundane, contaminating the signal you're actually trying to extract. So you begin subtracting, painstakingly, carefully, one source at a time. You subtract all the stars you can identify individually. Every star bright enough to show up as a point in the image, you catalogue and remove. You subtract all the galaxies you can identify individually, the ones bright enough to show up as little smudges or dots. You subtract the known artifacts of the camera itself, the various ways in which a detector can produce a false signal, a ghost, a scatter pattern from a source just outside the frame. And then after all of that, something is left. A faint residual glow, a background whisper. That residual, whatever it is the candidate cosmic optical background. Now the question is, what's actually in that residual? Because this is where it gets subtle. Some of what's left might genuinely be the COB, the integrated light of all the galaxies too faint to catalogue individually, all of them too dim to resolve as distinct smudges, but together contributing a soft, smooth, pervasive glow across the whole sky. But some of what's left might be other things that are hard to subtract cleanly. Scattered light from the bright stars and galaxies you did subtract, a little of their light spraying sideways through the optics in ways that are hard to fully model. Faint, diffuse structure in the Milky Way itself, starlight scattered by dust within our own galaxy, a soft luminescence that fills the sky at a very low level and is not easy to account for completely. This is not a simple measurement. There is no dial you can turn that says, COB only, please. Every number you pull out of that background glow is the result of a long, careful, contested chain of subtractions. And where you draw the line, what you decide to subtract and how thoroughly you subtract it, changes the answer you get at the end. This is worth holding in mind because it's the key to understanding why the New Horizons results became a controversy. Not a manufactured controversy, not a disagreement between people who don't trust each other, but a real methodological, scientific disagreement about a genuinely hard measurement in a genuinely hard environment. Now, the whole reason New Horizons is doing this measurement in the first place, rather than a telescope on Earth or in orbit near Earth, comes back to a single word: dust. Near Earth, the inner solar system is filled with fine particles of dust left behind by comets and asteroids and the slow grinding of rocky debris, drifting in a broad, flattened cloud around the Sun. When sunlight hits this dust, the dust scatters it in all directions, including toward us. The result is the zodiacal light, a faint, milky glow that runs along the ecliptic, the plane of the solar system. On a dark night, away from city lights, you can sometimes see zodiacal light with the naked eye, a pale, pyramid-shaped glow rising from the horizon along the path the planets trace across the sky. That zodiacal light, beautiful and mysterious as it is to see with your own eyes, is an absolute nightmare if you're trying to measure faint background glows from the entire universe. It's much, much brighter than the cosmic optical background. It drowns the signal completely, and it doesn't end at Earth. It extends through much of the inner solar system. Space-based observatories like Hubble, sitting just above Earth's atmosphere, still have to deal with it. The signal you're trying to measure is like trying to hear a single, whispered voice from the other side of a room while a party is happening right beside your ear. New Horizons, out at 60 AU, is past all of that. The zodiacal dust cloud thins out enormously as you move away from the Sun. By the time you're in the outer Kuiper Belt, it's essentially gone. The sky from where New Horizons sits has none of the zodiacal glow that haunts every measurement made near Earth. None of the airglow that Earth's own atmosphere adds to every ground-based telescope observation. The interplanetary clutter, the sunlight scattering background, the warm scattered foreground, all of it is gone. What's left is just the sky itself, the real sky. The sky as it would look if you could strip away everything human instruments have ever had to peer through. And from there, from that perfect, unprecedented dark, the measurement becomes possible in a way it simply isn't anywhere closer to home. This is what the New Horizons team understood. Out there, at 60 AU, LORRI is seeing something no instrument in human history has ever had the opportunity to see cleanly. A sky uncontaminated by the foreground glows that have always gotten in the way. But before we get to what the measurement actually found, it helps to understand the logic of what the measurement is trying to check, because the cosmic optical background doesn't exist in isolation. There's a way to predict what it should be. Astronomers have been taking deep images of the sky for decades. The deepest, most famous images are things like the Hubble Ultra Deep Field, where the Hubble Space Telescope stared at a tiny, tiny patch of sky, an area about the size of a grain of sand held at arm's length for hundreds of orbits, accumulating light over millions of seconds of exposure time. In that absurdly deep image, nearly every point of light that appeared turned out to be not a star, but a galaxy. Thousands of them in that one tiny patch, each one containing hundreds of billions of stars. From images like that, astronomers have been able to make very detailed catalogues of galaxies, how many there are at different distances, what shapes they come in, how bright they are, how their brightness changes with their distance and their age. And from those catalogues you can calculate, galaxy by galaxy, what the total optical background should look like, what the integrated light of all those galaxies, added up, should produce. It's a bit like trying to measure the total amount of money in a city's economy by counting every individual transaction you can see, and then checking whether the overall circulation of cash in the system matches what those individual counts would predict. If the direct measurement of the background glow matches the galaxy count sum, everything is consistent. All the light in the universe is accounted for. Every galaxy producing visible light has been counted, and the total adds up. If the direct measurement comes out higher than the galaxy count sum, something is missing from the count. There's light in the universe that isn't coming from any galaxy we've catalogued, and that gap, if it's real, is very interesting. It could mean that there are many, many more galaxies than we've counted. Billions of very faint, very dim, very spread out galaxies, each one far too faint to appear as a distinct object, even in the deepest Hubble image. But together, contributing a meaningful glow to the background. Galaxies we've been missing because they're just too dim for any individual count to catch, but collectively, they add up. That would mean our census of the universe is incomplete. That would mean the universe contains more stars, more light, more structure than our deepest surveys have captured. Not dramatically, catastrophically more, but meaningfully more. Or the gap could mean something else entirely, something much harder to explain with ordinary astronomy, but we're not quite there yet. What matters for this part of the story is the logic of the comparison. The Hubble galaxy count gives you a predicted background brightness. The LORRI measurement from 60 AU gives you an observed background brightness. Compare the two. If they match, the books balance. If they don't, something in the accounting is off. It sounds straightforward. Put those two numbers next to each other and read the result. But making that comparison cleanly requires that both numbers be as accurate as possible. The galaxy count from Hubble is extremely careful work, and the background measurement from LORRI is, as we've been exploring, extraordinarily difficult to get right. The residual background after subtraction is genuinely faint, far fainter than anything in everyday experience. We're talking about light levels measured in units called nanowatts per square meter per steradian, where a steradian is a measure of solid angle in the sky. The numbers involved are very small, single-digit or low double-digit small, and the question is whether those small numbers match the galaxy count prediction or exceed it. That comparison, made with more care and precision than any comparable measurement before it, was what the New Horizons team finally published. And the answer they got was not what most people expected. The darkness, when they measured it carefully with LORRI from out there beyond the dust, didn't match. The sky came back brighter than it should have been. Brighter than the known galaxies could account for. Not a lot brighter in absolute terms. We're still talking about extremely faint light. Light so faint that you and I could not come close to detecting it with any instrument available to us in daily life. But in astronomical terms, the excess was not small. It was, in the language of the early results, roughly comparable in magnitude to the entire contribution from all the known galaxies combined, roughly twice as bright as expected. That's a meaningful discrepancy. If the measurement is right and the excess is real, it means there's approximately as much optical light in the universe from unknown sources as there is from all the galaxies we have ever catalogued. That's not a rounding error, that's not a calibration issue. That, if true, would be saying something profound about how much of the universe we've been missing. The team, led by Todd Lauer, an astronomer at the National Science Foundation's Noyer Lab and a member of the New Horizons science team, published the results in the Astrophysical Journal in 2021. The measurement was careful, the methodology was detailed, the error bars were real but not large enough to make the excess disappear. The excess was, as far as the team could determine from that first careful analysis, genuinely there. And the question, naturally, was what was causing it. Two broad categories of explanation were available. The first was mundane, in the sense that it didn't require any new physics. If the cosmic optical background really is brighter than the galaxy count predicts, the simplest explanation is that our galaxy catalogues are incomplete. That there are billions of galaxies, perhaps very faint, very diffuse, very low surface brightness, spread across enormous areas of sky without ever forming a bright central concentration that our deepest surveys have been missing. Galaxies too dim to register as distinct objects even in the Hubble ultra-deep field, but numerous enough that their collective glow adds up to a significant fraction of the total background. That possibility is not exotic. The universe is very large and observations are never perfect. We have always known that our galaxy catalogues represent a sample, not a complete census. The question has always been how incomplete the sample is. If New Horizons found a real excess of background light, it would be suggesting the sample is more incomplete than previously thought. The second broad category was much more speculative, and the papers were careful to present it that way, as a speculative possibility rather than a leading explanation. But it circulated in the popular press in more dramatic terms. Some physicists have proposed that dark matter, the invisible material that makes up most of the matter in the universe but which we've never directly detected as a particle, might decay. Some dark matter candidates, exotic hypothetical particles, could, over very long timescales, convert their mass into ordinary photons, ordinary light. If this were happening throughout the universe, across the vast amounts of dark matter that fill galaxies and galaxy clusters and the filaments between them, it could produce a diffuse background of light, a glow from the decay of something invisible. That would be, to put it plainly, extraordinary. It would be new physics. It would be confirmation of a specific type of dark matter candidate. It would be one of the most significant discoveries in the history of physics. It's worth being honest about where that idea sits. It's a minority hypothesis. It's taken seriously by some physicists because it's grounded in real particle physics models, but it's far from the mainstream expectation. The mainstream expectation, if there's a real excess, leans toward the faint galaxy interpretation. But in 2021, when the first LORRI results came out, both explanations were genuinely on the table. The measurement was real, the excess appeared to be real, and what was causing it was an open question. Hold that open question in mind, because the story doesn't stop in 2021. The power source that keeps all of this possible, the reason New Horizons can still point LORRI at the dark sky and send back images, is a single radioisotope thermoelectric generator, RTG. It works by using the heat produced by the natural radioactive decay of plutonium-238 to generate electricity. No solar panels would function at 60 AU, where sunlight is more than 3,600 times fainter than at Earth. Solar panels that size would be impractical to build and impossible to deploy. The RTG is the only option, a compact, reliable, slowly diminishing source of power that needs no sunlight, no external input, nothing but the slow, steady decay of its radioactive core. It produces only a couple of 100 watts, roughly comparable to a few incandescent light bulbs. And that number is falling, slowly, as the plutonium-238 decays. It will keep producing useful power into roughly the late 2030s, though exactly how long depends on careful management. Every observation the team wants to make has to be weighed against the power budget. Every instrument that runs draws from a fixed and shrinking supply. This means New Horizons has a deadline, not an arbitrary one imposed by funding or bureaucracy, a physical one. The fuel for its power is running out. When it finally drops below the threshold needed to keep the instruments running, the mission ends. The spacecraft keeps going, keeps sailing outward forever, but it goes dark. No more data, no more images. That deadline gives the Cosmic Optical Background measurements an urgency that a ground-based observatory doesn't have. The longer they can keep LORRI running, the more observations they can stack, the more images they can average together to reduce noise, the cleaner the measurement gets. But the window for doing that is finite. The best measurements they can make are the ones they make before the power runs out, and they can't steer it in real time. At 60 AU, a radio signal traveling at the speed of light takes more than 8 hours to reach New Horizons from Earth. More than 8 hours. The round trip, sending a command and receiving confirmation that it arrived, takes over 16 hours. Nothing about the spacecraft's operation can be adjusted in anything resembling real time. Every sequence of observations is uploaded in advance, stored in the onboard computer, and executed automatically without any human input. The mission operators on Earth won't know if something went wrong until 8 hours after it happened. And returning the data, getting the images back to Earth for analysis, happens at kilobits per second. kilobits. The data rate from a 60 AU distance is glacially slow. Downloading even a modest set of imaging data, the kind of dataset needed for a careful background measurement, takes an extremely long time. This is part of why the published science from New Horizons tends to arrive well after the observations are made. The photons hit LORRI's detector, get stored on board, trickle back to Earth over months, and then are processed and analyzed for months more before a paper appears in the Astrophysical Journal. The gap between observation and understanding is measured in years, but the analysis does come, and in the years following the 2021 LORRI paper, the team, now including Mark Postman of the Space Telescope Science Institute and others, went back to the data with more care and more images. They refined the measurement. And the story took a turn. There was something they needed to look at more carefully, something in the subtraction process that hadn't been accounted for fully enough in the initial analysis. It's called diffuse galactic light, DGL for short. Even after you've subtracted all the individual stars and galaxies you can identify, even after you've removed the zodiacal dust glow entirely by virtue of being 60 AU from the Sun, there's another source of faint, diffuse illumination in the sky. It comes from our own galaxy. Starlight from the stars of the Milky Way, scattered by interstellar dust within the galaxy itself, produces a soft, broad, faint glow that spreads across the sky at a very low level. It's not the bright band of the Milky Way that you can see with the naked eye on a dark night. It's much fainter than that, a diffuse luminescence spread across the entire sky from dust particles in the interstellar medium, catching starlight and scattering it in all directions. Diffuse galactic light doesn't go away when you're 60 AU from the Sun. It's not from the solar system, it's from the galaxy. New Horizons is still inside the Milky Way. It will be inside the Milky Way for many human lifetimes to come. And so the DGL is still there in the background of every LORRI image, adding a faint glow that could easily be confused with the cosmic optical background if not properly subtracted. In the initial LORRI analysis, the DGL had been accounted for, but accounting for something doesn't mean getting it perfectly right. The DGL is itself a diffuse, faint, spatially varying phenomenon that's hard to model precisely. Its brightness varies depending on where in the sky you're looking, how much interstellar dust lies along that line of sight, and how the dust scatters light. The refined analysis by Postman, LORRI, and their colleagues looked more carefully at the DGL contribution. They used better models, better calibration data, and a larger set of images. And what they found was that the DGL had been somewhat underestimated in the initial measurement. When they accounted for it more thoroughly, the excess background glow shrank. It shrank quite a bit. The refined cosmic optical background value converged toward roughly 11 nanowatts per square meter per steradian. And that number, with its uncertainties, was broadly consistent with what you'd predict from the deep galaxy counts, from the Hubble Ultra Deep Field and similar surveys. The gap, the excess that had looked so alarming in 2021, had narrowed substantially. Some headline writers declared the mystery solved. The anomaly, they said, was largely explained by underestimated Milky Way dust. The universe was not, after all, too bright. It was a satisfying resolution. A careful, methodical investigation of the measurement had traced most of the anomaly to a known, mundane source. Diffuse galactic light, interstellar dust scattering Milky Way starlight. Nothing exotic, nothing new, just a careful accounting of something that had been slightly undercounted the first time. Clean and tidy. But science is rarely as clean and tidy as a headline would like it to be, because the story didn't stay solved, and that is where we're going next. Into the third chapter, the one that's still being written right now, the chapter where independent teams looked at the same data or at similar data and arrived at a different conclusion about whether the dust correction was complete enough. The chapter where the question is genuinely open again. But right now, let the earlier parts of this settle. The journey from Earth in January 2006, the fastest launch ever attempted, the Moon's distance in 9 hours, and then years of patient coasting into the outer darkness. The arrival at Pluto, the heart-shaped plain of nitrogen ice, the mountains of water ice standing up from the smooth white, a world appearing out of the dark for the first time. Then the long coast to Arrokoth on New Year's Day 2019, the gentle snowman frozen in place for 4.5 billion years, a fossil from the solar system's very first moments. And then the pivot, the thing that most stories never reach. New horizons moving past both of those destinations, still moving, still working, pointing its planetary close-up camera at the darkest patches of empty sky it could find, trying to weigh the light of the whole universe, a measurement that was easier out there than anywhere else humans had ever managed to look, and harder than it sounds from any distance. The comparison. The galaxy count from Hubble, a predicted brightness, the LORRI measurement, an observed brightness, and the unsettled result, the 2021 finding of a real excess. The 2024 analysis tracing much of it to Milky Way dust, the reopening that came after. All of it unfolding very slowly, very carefully, by a small team of scientists working with images that take years to arrive, from a spacecraft running on 200 watts of slowly fading plutonium heat, 8+ hours away by radio at the speed of light. Rest your eyes, we have more to explore, the story of what happened when the case reopened, and what it means that the question of whether the universe is too bright is still genuinely unresolved right now, tonight, while you're listening to this. That's the part we're moving toward. Quietly. No rush. The spacecraft is still out there. The data is still coming. The argument is still alive.
And somewhere in the middle of all of it, there's a passenger aboard New Horizons who has been making this particular journey for a very specific reason. But that part comes later, when we're ready.
For now, let the numbers drift quietly. 60 astronomical units. 8.9 billion kilometers from home. A spacecraft moving outward at roughly 3 astronomical units per year, with a camera never designed for this purpose, and a power source that won't last forever, trying to answer one of the most fundamental questions the sky can ask. Is there light in the universe that we've been missing? The answer, as best as we know it right now, is possibly. And that's more interesting than either yes or no would be on its own. So let's go there now. Let's move into the anomaly itself. It began, as many things in science begin, with a number that didn't behave. The year was 2021. The team was led by Todd Lauer, an astronomer at the Noyer Lab facility in Tucson, Arizona, working alongside colleagues from the broader New Horizons science team. They had spent considerable time, months really, doing something that sounds almost absurdly simple when you describe it quickly, and is anything but when you sit with the details. They pointed LORRI at the dark, not at Pluto, not at Arrokoth, not at any particular object at all. They pointed the Long-Range Reconnaissance Imager, a camera built with extraordinary precision to photograph ice mountains and nitrogen plains from tens of thousands of kilometers away, at patches of sky that were deliberately chosen to be as empty as possible. Regions well away from the glow of the Milky Way. Regions with no bright stars in the frame. Regions that looked, to every reasonable measure, like nothing. Like black. And then they waited for the photons to accumulate. Long exposures, patient ones. The kind of waiting that takes hours of telescope time and then months of analysis. And then they subtracted everything they could account for. Every catalogued star, every resolved galaxy visible in the frame, every artifact of the instrument itself. the faint internal glow that any sensitive camera produces just by existing, the charge bleeding from bright pixels, the subtle signatures of the detector. They removed all of it, layer by layer, with enormous care. What remained, they knew, would be the candidate cosmic optical background, the glow that was left when everything else was gone, the light that belonged to no single source they could name. What remained was not nothing. It was not even close to nothing. The light that came back once all the accounting was done was roughly twice as bright as all the known galaxies in the universe could explain. Twice. When Todd Lauer and his colleagues compared their direct measurement against the independent estimates of how much light the entire catalogue of observed galaxies should be producing, estimates built from deep surveys, from the Hubble Ultra Deep Field and its successors, from decades of painstaking galaxy counts, the numbers didn't match. The sky was brighter than the galaxies, not by a little, by a factor of around 2. In the technical literature, this was called the anomalous diffuse flux. In plain language, it was this: there was more light than there should be, on the order of roughly 16 nanowatts per square meter per steradian of excess, a unit that sounds abstract until you understand that this is a measurement not of a beam of light, but of the glow of a patch of sky, the diffuse, sourceless luminosity of empty space itself. 16 units where 0 was expected. 16 units that had no address. The paper was published in the Astrophysical Journal. That's the flagship journal of American astronomy, the place where measurements are peer-reviewed before they become part of the scientific record. This wasn't a tweet, it wasn't a press release full of maybes, it was a submitted, reviewed, accepted measurement, and the measurement said the darkness wasn't dark enough. Pause on that for a moment, because it's genuinely strange. You've left the solar system behind, you've left the dust that glitters around the sun, you've left the atmosphere that shimmers and blurs. You are 8+ billion kilometers from home, in the cleanest dark any human instrument has ever reached, and you point your camera at the emptiest patch of sky you can find, and the sky glows back at you. Faintly? Yes. In units that would make your eyes see nothing, but there, real, measurable, statistically undeniable. Where is it coming from? That was the question. And it was, as questions go, a genuinely enormous one. Because if the cosmic optical background, the summed accumulated light of every galaxy that has ever existed, is twice as bright as your census of known galaxies predicts, one of two broad things is true. Either the census is wrong, either there are galaxies or diffuse sources of light that your surveys haven't found or haven't counted properly, or the physics is wrong, or at least incomplete. The first possibility sounds modest. Oh, we missed some galaxies. But sit with the scale of it. We're not talking about missing a few faint smudges on the edge of a photograph. We're talking about the possibility that the universe contains roughly as much galaxy light again as we've been able to catalogue. That our surveys, even the extraordinary ones built from thousands of Hubble exposures stacked together over weeks, were missing half the light. That the universe has a population of stars, or entire galaxies, so faint, so diffuse, so spread out across the sky that they slip beneath every threshold we've set. The second possibility is harder to say out loud without it sounding sensational, but the literature mentioned it, and it wouldn't be honest to leave it out. The long-shot explanation, new physics, some process producing photons that isn't on the list of known astrophysical sources. The most commonly discussed candidate in this category was the decay of dark matter particles. Dark matter, which makes up the majority of the universe's mass and which we've never directly detected, remains genuinely unknown in its microscopic nature. Some theoretical models predict that certain dark matter candidates, particles with specific properties, that would slowly decay over cosmic time, and that decay would release photons. Light. a faint, sourceless glow distributed across the whole of the universe, coming not from any galaxy, but from the dark matter web itself. And you'd never find it by looking at galaxies. It would just be there, diffuse, everywhere, belonging to nothing. Now, to be clear, this was not the consensus explanation. No one was announcing the discovery of dark matter decay. The excess was real, its source was unknown. Exotic physics was flagged as a possibility, not a conclusion. The mainstream scientists who discussed it, including Lauer's team, were careful to frame it that way. An anomaly is not a discovery. An unexplained measurement is the beginning of a question, not the answer to it. But the question was serious, and it was happening at the most distant and sensitive light-measuring instrument humanity had ever deployed. Let's stay with the spacecraft for a moment, because there's something important about the situation. New Horizons is actually in right now, while these measurements are being taken and the arguments are being had. Something that gives the whole thing an edge of urgency that cold numbers alone don't convey. New Horizons runs on a single radioisotope thermoelectric generator. You can think of an RTG like this. Imagine a glowing coal inside a thermos, and the thermos converts the heat of that coal into electricity. Except the coal is plutonium-238, a radioactive isotope, and instead of burning it emits heat through the slow, steady decay of its atoms, a process you can't speed up and can't slow down. The heat is reliable and constant and entirely unrelated to sunlight, which is why it works 60 astronomical units from the sun, where solar panels would be essentially useless. But here's the thing about radioactive decay. It doesn't stay constant forever. Plutonium-238 has a half-life of about 87.7 years, which means roughly every 88 years, half of what remains has decayed into something else, and the heat output drops by half. New Horizons has been flying since 2006. By the mid-2020s, its RTG was producing only a couple hundred watts of electrical power. To put that in human terms, a couple hundred watts is roughly what it takes to run 2 or 3 bright, old-fashioned incandescent light bulbs. Not a household, not even a room full of lights, 2 or 3 bulbs. That's the power budget for a spacecraft doing science 8 billion kilometers from Earth. And it's declining. Every year, the output drops a little more. Every year, the engineers have to decide which instruments stay on and which get turned off, which heaters are essential, and which can be sacrificed to save a few watts for the science instruments. Current projections suggest the RTG will provide enough power to operate the spacecraft, to keep the essential systems alive and the key instruments running, into roughly the late 2030s, if the power is managed with care. That gives New Horizons something like another decade of active science from where it stands now. Maybe a little more, maybe a little less, depending on what the team decides to prioritize. That's not forever. And for measurements like the Cosmic Optical Background, measurements that require long exposures, careful pointing, multiple images at multiple times to build statistical confidence, a decade is not an enormous amount of time, especially when you factor in what comes next, which is the light lag problem. Right now, as New Horizons orbits outward through the dark, it is roughly 60 astronomical units from Earth. 1 astronomical unit is about 149.6 million kilometers. At 60 AU, the straight-line distance from the spacecraft back to the antennas of the Deep Space Network, the radio dishes in California and Spain and Australia that serve as its communication link, is roughly 8.9 billion kilometers. And radio waves, like all electromagnetic radiation, travel at the speed of light, about 300,000 kilometers per second. Do the arithmetic and you find that a radio signal from Earth takes more than 8 hours to reach New Horizons, more than 8 hours one way, which means the round trip, send a command, wait for acknowledgement, takes over 16 hours, more than half a day. This is not a situation where you can sit in a control room and steer the spacecraft the way you'd steer a drone. You can't nudge it left and say, oh, actually, go a little right now. Whatever you told it to do yesterday is already in motion. If something goes wrong, you find out 8 hours later. If you need to adjust, your adjustment arrives 8 hours after that. The spacecraft flies on stored command sequences. The team uploads a detailed set of instructions: point here, expose for this duration, rotate, expose again, record. And New Horizons executes those instructions on its own, independently, across the weeks and months before the next command sequence arrives. It's a spacecraft that, in a very real sense, has to know what it's doing before it does it. It makes no room for improvisation. And then there is the downlink. All that precious data, all those carefully accumulated photons from the dark patches of sky, all those measurements of the cosmic optical background, has to travel those same 8+ billion kilometers back to Earth. And it can only travel so fast, and it can only carry so much information per second through the radio link at this distance, even with the most powerful antennas we have. The data comes back at kilobits per second, not megabits, not gigabits, kilobits. To give you a sense of scale, a single high-resolution photograph on your phone might be 5 or 10 megabytes, or 40 to 80,000 kilobits. New Horizons from 60 astronomical units can send back data at a rate of a few kilobits per second, which means it takes hours or days to return what you could send from your kitchen in a second. This is why the science from New Horizons arrives on timescales of years, not days. The images used in the 2021 LORRI analysis had been collected over a period of time, slowly accumulated, slowly downlinked, slowly assembled on Earth. The processing and analysis took additional months. The peer review took additional time. By the time the result appeared in the Astrophysical Journal, the photons that created the measurements had long since been captured. The spacecraft had already moved outward by another chunk of distance. The team had already begun planning the next round of observations. This is not a fast science. It can't be. The distance won't allow it. And this is part of what makes the anomaly with the excess glow in the dark carry a particular kind of weight. It wasn't a quick observation. It wasn't a casual measurement. It was the result of years of careful work at the very edge of what the instrument could do, sent back a few thousand bits at a time across the dark, analyzed with the full force of the available mathematics and calibration science, and it still came back weird, twice as bright as the known universe. The anomalous diffuse flux, real, measured, unexplained. So what were the explanations on the table? The first, and the one that most astronomers considered more likely even at the time, was what you might call the mundane but profound option. Not new physics, not dark matter decay. Something considerably more boring, and in its own way, considerably more unsettling. We have miscounted the light. The universe contains a vast population of galaxies, hundreds of billions at minimum by most estimates, and probably far more when you account for the faintest and smallest. The Hubble Ultra Deep Field, one of the most extraordinary images in the history of astronomy, is a single, tiny patch of sky observed for hundreds of hours of exposure time, and in that tiny patch, a region about as wide as a grain of sand held at arm's length would cover, there are roughly 10,000 galaxies visible. 10,000 entire galaxies in a patch of sky so small you'd need to squint to see it. And yet those are the ones bright enough to resolve individually. The threshold for what Hubble can detect, even in its deepest exposures, is not zero. There is a floor. Below the floor, galaxies are too faint to count, too diffuse, too distant, too small. They blur below the noise level of even our most sensitive instruments, and we count them as sky rather than as source. If there are enough of those below-threshold galaxies, enough faint, low-surface brightness objects spread thinly across the universe, their combined light could contribute meaningfully to the cosmic optical background without any single one of them appearing in our catalogues. And if we then compare our directly measured Colby to our catalogued galaxy counts, we'd see an excess, a glow from sources we haven't been able to name. The universe in this scenario is not doing anything unusual. We are just not seeing all of it. Our surveys are incomplete in a way that matters. This is both reassuring and quietly humbling. Reassuring because it doesn't require new physics. Humbling because it would mean our census of the cosmos, our most ambitious attempt to count what's out there, is still missing something, that the universe has more to it than we can directly photograph. That there is, in a very real sense, hidden light. The second explanation, the exotic one, was mentioned in the literature and deserves to be treated honestly rather than either hyped or dismissed. Some theoretical frameworks predict that certain species of dark matter, the invisible, non-luminous material that makes up the vast majority of the universe's mass, whose nature remains entirely unknown at the particle level, could decay over cosmic time. Not explosively, not dramatically, just slowly, atom by notional atom across the eons, each decay event releasing a photon or a small cascade of energy that eventually becomes photons, light. If this is happening, the glow wouldn't come from any particular galaxy. It would come from the dark matter halos that surround galaxies, from the filaments of dark matter that connect galaxy clusters, from the voids between them. It would be diffuse, sourceless, distributed. It would look, in a measurement, like a faint background glow that didn't match any catalogue. It would look, in other words, a bit like what Lauer's team measured. But, and this is the part that matters, this was a minority hypothesis. The kind of thing scientists mention carefully, with appropriate qualification, not because they believe it is likely, but because intellectual honesty requires putting all the options on the table. The excess was real, the cause was unknown. Dark matter decay was one of the things it could, in principle, be. It was not what most people in the field thought it probably was. The most important thing to hold on to here is that the measurement had been made, the question was in the room, and for a few years it stayed open. And then, somewhere in the period between 2022 and 2024, the analysis got better. This is how science actually works at its best. Not a single dramatic moment of revelation, not a press conference where everything is overturned. A process, a slow, careful, iterative reckoning with the numbers, going back to the images, improving the calibration, accounting for sources that had been imperfectly subtracted the first time, checking and rechecking until the picture sharpened. The work was led in significant part by Mark Postman, an astronomer at the Space Telescope Science Institute in Baltimore, working alongside Todd Lauer and other colleagues. They went back to the LORRI images, they went back to the calibration models, they went back to the list of things being subtracted, and they found something. One of the foreground sources, one of the layers of contaminating light that had to be stripped away before the true COB could be measured, had been underestimated. Not dramatically, not by orders of magnitude, but by enough to matter. And the source was the Milky Way itself. This particular source of contamination has a name, diffuse galactic light, or DGL. It refers to the faint glow produced by starlight from our own galaxy, light from the billions of stars in the Milky Way, scattered and redirected by the interstellar dust that fills the disk of the galaxy. You can think of it the way you'd think of fog on a highway at night. When headlights shine into fog, the fog glows. Not because the fog itself is a light source, but because the tiny water droplets scatter the light in all directions, including back toward you. The interstellar dust of the Milky Way does something similar with starlight. It catches the light from stars and scatters it diffusely across the sky. From the vantage point of New Horizons, 60 astronomical units out, well above the ecliptic plane, but still embedded in the galaxy, this scattered light is present everywhere. It doesn't come from a point source you can locate and subtract. It's a soft, pervasive, low-level glow distributed across the whole sky, and it is extremely difficult to model precisely. How bright is it in this particular direction? How does it vary with galactic latitude? How much of what LORRI is recording is actual COB, and how much is this faint galactic fog? When Postman, Lauer, and their team went back with improved models of the diffuse galactic light, better estimates of where the Milky Way's scattered light was and how bright it was in the directions LORRI was looking, the excess shrank, not to zero, but significantly. The measured COB value, once the diffuse galactic light was more carefully accounted for, moved downward from the initial result. It converged towards something on the order of 11 nanowatts per square meter per steradian, a number that was, within the uncertainties of both the measurement and the models, broadly consistent with what the catalogued galaxies should be producing. The galaxy counts and the direct measurement were, if not perfectly matched, at least no longer separated by a factor of 2. Some headlines, when this refined analysis began to appear, described it as the mystery solved, the glow explained. Scientists thought the universe was twice as bright as it should be, but it turned out to be a measurement artifact, a foreground we hadn't properly accounted for, and now that it's corrected, everything makes sense. It's a satisfying story, clean, resolved, tidy. And for a moment it seemed like that might be where things settled. But here's where you need to hold the story carefully, because this is the part that the easy headlines tend to skip. The improved analysis was not the final word. It was an important step, a significant correction, a genuine piece of scientific progress. But science, especially at this level of precision, rarely ends with a single improved analysis. The corrections Postman and Lauer's team made were based on specific models of the diffuse galactic light, specific assumptions about how the Milky Way's scattered starlight was distributed and how bright it was in the relevant sky patches. And models, even very careful ones, have uncertainties built into them. Different teams, using different models and different approaches to the same fundamental problem of separating the foreground from the background, have continued to work on the data. And some of those independent analyses, published or circulated in the 2024 and 2025 period, still find a residual excess. Not as large as the original factor of 2 anomaly, but something, a faint, persistent glow that doesn't quite go away even after the dust correction is applied. The case, in other words, did not fully close. It got smaller, it got more constrained. The exotic options, the dark matter decay scenarios, became less necessary. Because if much of the excess was just Milky Way dust, you don't need new physics to explain it. But much of the excess is not the same as all of the excess. And the remaining fraction, whatever it is, small, uncertain, fought over by careful scientists with different models, is still, as of the mid-2020s, not cleanly explained. Is the universe too bright? Maybe. Probably less than we thought in 2021. But the honest answer, the one that actually matches the state of the field right now, is we don't know yet. And that uncertainty is not a failure. It's the frontier. It's where the science actually lives. Breathe that in for a moment. Settle with it. Because this is the thing about real scientific questions, at least the ones that matter, the ones that touch something fundamental about how the universe is put together. They rarely flip cleanly from mysterious to solved. They move instead through a slower, more textured process. A measurement is made, it's refined, it's challenged. The challenge is partially answered, a residual remains. The residual is measured more carefully. And somewhere along that path, gradually over years and decades, the picture sharpens enough that you can finally say something with confidence. We are somewhere in that process right now, not at the beginning, not at the end. And New Horizons is still out there, still measuring, still sending back a few thousand bits of data at a time across the dark. The power is declining, the window is real, but the instrument is still working. And the team is still doing the careful, slow, painstaking work of trying to understand what the dark is actually made of, what glow, if any, hides in it that the known universe hasn't explained. That's what the spacecraft is doing tonight while you're listening to this. Its stored command sequences are cycling through whatever observations the team planned months ago. Its RTG is producing a couple hundred watts, slightly less than it was producing last year, slightly more than it will produce next year. Its downlink is trickling data back to Earth at kilobits per second, slowly filling the queue of information that analysts will spend months working through. And somewhere in that trickle, in those carefully captured images of empty dark sky, in those long exposures pointing at patches of nothing, there may be more data that will eventually help answer the question, or refine the question, or replace the question with a better one. That's the honest state of things as of right now. It's worth pausing on the method one more time because it's easy to miss how strange and elegant it is. What the team is doing at the most basic level is this. They are trying to measure the total light output of the entire universe by staring at a patch of sky that looks empty and measuring how bright the nothing is. Every photon that arrived at LORRI's detector from one of those dark patches traveled some portion of the path from its source, whether a distant galaxy, a faint dwarf galaxy, below cataloging thresholds, a patch of Milky Way dust catching starlight, or some hypothetical exotic process, across space to the camera. LORRI collected those photons over the exposure time. The total brightness, after subtracting the known contributors, is a record of everything that ever glowed. That's what the cosmic optical background really is when you strip away the jargon. It is the accumulated record of every star that ever lived and died. Every galaxy that ever formed, from the first ones that coalesced in the early universe down to the ones forming right now. Every photon they ever emitted that still travels through space, redshifted and stretched by the expansion of the universe, but still present, still arriving, still depositing tiny fractions of energy into the detector of a camera 60 astronomical units from Earth. Measure the cob and you are, in a sense, taking a receipt for the universe, an audit of all the light there ever was. And the audit doesn't quite balance, not yet, not clearly. The numbers are closer than they were in 2021, but the ledger isn't fully reconciled and the scientists working on it are still carefully checking their sums. What does it mean if it never fully reconciles? If there really is more light than the known galaxies can produce? The most likely explanation, even now, even after the dust correction, is not the dramatic one. It's the quiet one, the one that says, we are still not seeing all the universe. There are galaxies, or something like galaxies, or something like diffuse star fields, so faint that all our surveys together haven't been able to measure them individually. They're not exotic, they're just dim. So dim that even the Hubble Ultra Deep Field, a photograph made from hundreds of hours of exposure time in the most sensitive space telescope ever built, didn't register them as individual points of light. They dissolve into the background, but their light doesn't disappear. It adds up, it reaches new horizons, and it shows up as an excess. The universe in this reading is larger in some practical sense than our inventories suggest, not geometrically larger, but richer, fuller. There is more structure, more stellar mass, more accumulated nuclear burning history than we've been able to directly catalogue. That's not nothing. In fact, that's profound. It would mean that our best maps of the cosmos, our most ambitious sky surveys, our deepest images, are still incomplete in ways that affect the fundamental accounting of the universe's contents. And the only instrument currently capable of measuring this cleanly from the right place in space is a planetary exploration spacecraft launched in 2006, running on a battery it shares with no one communicating home at the speed of light, 1 kilobit at a time. But here's where the story gets strange again. Because in 2024 and into 2025, independent teams came back to the measurement, not to the 2021 result, to the corrected one, the one that had accounted for the diffuse galactic light, the one that had been widely framed as the resolution. And what they found when they worked through the numbers with their own methods and their own models is that the excess didn't entirely go away. Not the full doubling from 2021, that part really did shrink. The dust correction was real and it mattered, and it did bring the measurement meaningfully closer to what the galaxy counts predict. Nobody is disputing that, but closer is not the same as equal. There is still, in the most careful independent analyses published in 2024 and 2025, more diffuse optical light arriving at LORRI than the sum of the known, catalogued galaxies can cleanly account for. A residual. Not as alarming as the original factor of 2 excess, but real, stubbornly, persistently real, and not yet explained. What this means is that the headline that went around in 2024, the mystery solved story, the it was just dust story, was slightly ahead of itself. Not wrong about the dust was underestimated, that finding stands. But resolving part of an anomaly is not the same as resolving the anomaly, and the scientific community is in the uncomfortable position that the remaining residual doesn't have a clean home yet. So where does that leave us? Right here, in the genuinely unresolved middle of a live scientific argument. The 2021 result was a real measurement of a real excess. The 2022 to 2024 analysis found that a significant portion of that excess came from Milky Way starlight scattered off interstellar dust, the diffuse galactic light that had been underestimated in the original accounting. That part is consensus now, but independent groups examining the same data or extending the analysis further are still finding a gap between the direct Kolbe measurement and the galaxy catalogue sum, a gap that the dust correction doesn't fully close. Whether you call the universe too bright right now depends on whose analysis you're reading, what assumptions went into their dust model, and how generously you're willing to draw the error bars. That's not a cop-out. That's science at the edge of what is currently measurable. This is what it looks like when a question is genuinely open, not dramatized for a documentary, not simplified into a tidy conclusion, but actually, honestly, as of the time you are listening to this, unresolved. And there's something important to sit with in that. We live in an era of enormous scientific confidence, and rightly so. We know the age of the universe to a fraction of a percent. We can image a black hole shadow 55 million light-years away. We have mapped the cosmic microwave background to enough decimal places that it took years just to publish the results properly. Science has done astonishing things. And yet, whether there is more light than we can account for in the visible universe, that question is currently sitting in the inbox of a 20-year-old spacecraft that costs about as much to operate as a mid-tier office building, being asked through an antenna dish that takes 8 hours to receive a reply by a team of scientists who have to wait years for the data to trickle back at a few kilobits per second. The universe is big. The question is specific. And right now, the best instrument humanity has for answering it is New Horizons. That is not a metaphor. That is the literal operational state of the measurement as of the mid-2020s, and it has a deadline. New Horizons runs on a single radioisotope thermoelectric generator, an RTG fueled by the radioactive decay of plutonium-238. When engineers talk about it, they describe it producing only a couple of 100 watts, less than the light bulbs in an average living room. And that number is not constant. Plutonium-238 has a half-life of about 88 years, which means the power output declines slowly but continuously. Year by year, the RTG produces a little less. The team has to decide with increasing care which systems to keep running and which to let go dark. Current projections, and these depend on how the team manages the remaining power, how many instruments they keep alive, how many systems they allow to hibernate, suggest the RTG can keep New Horizons operable into roughly the late 2030s. That gives the spacecraft about another decade of useful science. A decade sounds like a long time. In some ways it is. That's another 30 AU of travel, another several years of data collection from the cleanest dark sky any instrument has ever seen. But it's not unlimited, and the COB measurement gets harder, not easier, as you try to squeeze it tighter. More images, more calibration, more careful modeling of the remaining foregrounds. All of that takes time and data, and the data arrives slowly, and the window to collect it is finite. So when scientists argue about whether the excess is real, they're not arguing in the abstract luxury of unlimited future observations. They're arguing with a clock running, and the clock is plutonium. Now, before we sit with the honest uncertainty of where the science stands, let's take a moment to look at the lonelier part of this picture, because New Horizons does not travel in well-charted company. There are 5 spacecraft total on trajectories that will carry them permanently out of the solar system, out beyond the reach of the sun's gravity, into the interstellar medium, and eventually, over millions of years, into the galaxy itself. 5. In all of human history. The first 4 were Pioneer 10, Pioneer 11, Voyager 2 and Voyager 1. They launched in the 1970s, all 4 of them, on missions that could barely have imagined what they'd eventually become. Pioneer 10 was the first human-made object to pass through the asteroid belt and fly by Jupiter. Pioneer 11 followed it and kept going past Saturn, out into the dark. Voyager 1 and Voyager 2 visited the outer planets in the Grand Tour, Jupiter, Saturn, Uranus, Neptune, and kept flying afterward, carried by the same momentum, now beyond the planets and into the space beyond. Voyager 1 is the most distant human-made object ever built. As of now, it has passed the 160 AU mark, more than twice the distance New Horizons has covered. At that distance, it is technically in interstellar space, past the heliopause where the sun's solar wind finally gives way to the broader galactic medium. Scientists have detected the actual plasma of interstellar space through Voyager 1's instruments, but Voyager 1 cannot see anything. Its imaging cameras were powered down decades ago, not because the mission ended, because the team had to make choices and the cameras were no longer justified when there was nothing nearby to photograph and when the power required to run them was needed elsewhere. The same is true for Voyager 2. The same is true for the Pioneer spacecraft, which fell silent entirely. Pioneer 10 last contacted in January 2003, Pioneer 11 in 1995. They are out there somewhere, sailing in directions we know, carrying their famous golden plaques with diagrams of where they came from and what we look like, silent as stones. None of them can look at the sky. That's the lonelier part. 5 spacecraft escaped the solar system. 4 of them are blind. The only one with a working, sensitive optical camera, or the only one that can actually point at the sky and make an image of the darkness around it, is New Horizons. A planetary spacecraft built to photograph Pluto, now doing cosmology from the edge of the solar system because it happens to be the only instrument out there capable of it. Voyager 1's power will last into the late 2020s or so, but there is nothing left to photograph with it. It listens and measures plasma and magnetic fields, and that is remarkable and valuable science. But it cannot do what LORRI does. It cannot count the photons of the cosmic optical background. So when the question is asked, is there a place in the universe from which you can take a clean measure of all the light ever made? The answer right now is yes. roughly 60 AU from the Sun, moving outward at 3 AU per year. Running on a slowly dying power source, one camera, one team, one window, one team, the extended mission for New Horizons was approved to continue science operations through at least the late 2020s. Heliophysics, observations of the outer heliosphere, the structure of the solar wind in the deep outer solar system, measurements of interstellar dust streaming inward across the boundaries of the heliopause, and, critically, continued imaging of the dark sky, COB measurements refined with more data, more images, more careful calibration. The team has not stopped. The camera has not been capped. And there is another possibility the team has not entirely given up on. After Arrokoth in 2019, New Horizons was in a part of the Kuiper Belt that had already been thoroughly surveyed. The chance of finding a new, close flyby target, a Kuiper Belt object whose orbit would intersect New Horizons' path within the spacecraft's remaining fuel budget, was much harder than it had been before the Arrokoth encounter. You can't steer the spacecraft dramatically. You work with what the fuel allows, and the fuel is not unlimited. The team used the Subaru telescope in Hawaii to search for candidate Kuiper Belt objects, faint, distant worlds sitting in the narrow corridor New Horizons could conceivably reach. The search was real, the effort was genuine, but as of the mid-2020s, no second flyby target has been confirmed. It remains possible, in principle, that the right object is out there at the right orbital position, but it has not been found yet, and the window is not eternal. So for now, New Horizons flies without a destination. It is not heading toward anything. It is heading away from everything familiar and using its time, the time it has before the RTG fades too much to justify operations, to look at the darkness and measure what's in it. That is, when you sit with it, a strange and beautiful mission, built to go somewhere specific, now going nowhere specific. Built to take close-up pictures of a particular place, now staring into the void between galaxies. Built by people who wanted to see Pluto, and now returning data about whether the fundamental inventory of the universe is correct. Science rarely goes where it plans. And now, here, this is the part that tends to stay with people. Wherever you are as you listen to this, whatever lamp is still on or whatever window is dark outside, think about what the cosmic optical background actually is for a moment. It is the sum of all the light that every star in every galaxy has ever produced across the entire history of the universe and sent outward in every direction, including toward us. It is not just the light of the galaxies we can see tonight with a telescope. It includes the galaxies that formed when the universe was young and whose light has been traveling toward us for 10 or 11 billion years. It includes the light from stars that died before our sun existed. It includes the glow from galaxies that are so far away and so old that their light has been stretched and dimmed by the expansion of space itself. All of that light, from everywhere and everywhen, passing through space, eventually arriving at a detector. That is the cosmic optical background, and the cosmic microwave background, which you may have heard of, the faint afterglow that fills the sky in microwave wavelengths, sometimes called the echo of the Big Bang. That is a different thing. The CMB is the first light. It is the glow that was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely for the first time. The CMB is the universe's beginning, encoded in radiation. The COB is the universe's history since then, since those first atoms. Every star that ignited, every galaxy that assembled, every nuclear furnace that burned hydrogen into helium and helium into heavier elements, every supernova that scattered those elements outward, all of it left a trace in visible light. The COB is that trace accumulated. Together, the CMB and the COB-E bracket the whole story. First light, and all the light since. To count the COB is to audit all the stars that ever lived. And if the count comes back too high, if there is genuinely more light arriving than our catalogues of known galaxies can explain, then there are stars, or stellar systems, or entire galaxies unaccounted for in our senses of the universe. Sit with that. Not as a frightening thought, as a generous one. The universe is possibly even richer than we knew. Not smaller, not stranger in a threatening way, just fuller. More history, more burning, more structure than all our best surveys have so far managed to capture. The Hubble Ultra Deep Field, that famous image made from hundreds of hours of staring at a patch of sky the size of a grain of sand held at arm's length, collecting light carefully and patiently until galaxies thousands of times too faint to see any other way revealed themselves. That image contained 10,000 galaxies. 10,000. In a grain of sand's worth of sky, and it might still not be enough. The diffuse background might include light from galaxies too faint and too spread out to show up even in that image as individual resolved sources. Their light comes anyway. It travels, it arrives, and LORRI catches it. There is something almost meditative about that once you get used to it. A camera the size of a suitcase spinning through the dark at 13 kilometers per second, pointing at the emptiest patches of sky it can find, and patiently collecting the photons that arrive there. Photons that have been traveling for billions of years. Photons that left their source before the Earth existed, before the Sun ignited, before the Milky Way finished assembling into the spiral shape it has today. They travel all that time, all that distance, and they end up on a camera chip aboard New Horizons. At 60 astronomical units from the Sun, the light of the Sun itself is reduced by more than 3,600 times compared to what you feel on a warm afternoon at Earth. Now that's not a metaphor, it's geometry. Sunlight spreads outward in all directions, and the same total energy that passes through a sphere 1 AU across has to cover the surface of a sphere 60 AU across. The area scales with the square of the distance. 60 squared is 3,600. The Sun, from where New Horizons sits, is still the brightest star in the sky, but it is a star, a very bright star, not a nearby furnace. You would not feel its warmth on your skin. And yet it is warm enough through the plutonium to keep the instruments running. Barely, but running. It is a strange kind of survival, not thriving, not comfortable, but working, persistent. Doing the science it came out here to do in the cold and the dark and the distance, with the power it has left. And now the part of this story that has stayed with me. The part I want to leave you with. There is a passenger aboard New Horizons. When the spacecraft was built and fitted and prepared for launch, a small container was incorporated into its structure. Inside the container, 1.5 ounces of ashes, the cremated remains of Clyde Tombaugh. Clyde Tombaugh was born in 1906 in Illinois. He grew up on a farm, built his own telescopes from scraps and spare parts, and taught himself enough astronomy to get a job at the Lowell Observatory in Flagstaff, Arizona. He was 22 years old when he arrived. In February 1930, after months of painstaking work comparing photographic plates of the sky, looking for a tiny dot of light that moved slightly against the background stars between one night and the next, he found it. A new world at the edge of the solar system, eventually named Pluto. Tombaugh spent the rest of his life associated with that discovery. He lived long enough to see Pluto reclassified, to see it demoted from full planet status in 2006. The same year, New Horizons launched. He did not quite see the reclassification, though. He died in 1997, 9 years before the launch. But his family was there, and when the question was raised of what to put aboard, what human thing should ride along on the mission to explore the world Clyde Tombaugh found, the answer was clear. He goes with it. So on July 14, 2015, when New Horizons swept within 12,500 kilometers of Pluto's surface and photographed the nitrogen ice plains of Sputnik Planitia and the mountain ranges of water ice and the vast heart-shaped formation now called Tombaugh Regio, named for him, the man who discovered Pluto was physically there. His ashes flew past his world. And then New Horizons kept going, past the Kuiper Belt, past Arrokoth, that frozen snowman of a contact binary, the most distant object explored up close at the time, past the familiar territory of the solar system into the realm where the sun is just a star, and the planets are memories, and the darkness is as clean as darkness gets. And Clyde Tombaugh kept going too. He is out there right now, as you listen to this, traveling at roughly 13 kilometers per second, 60 astronomical units from the sun, in a container about the size of a small box, aboard a spacecraft staring at the oldest light in the universe. The man who mapped the edge of the solar system is sailing past it, into the dark, forever. I find that thought almost impossible to hold without something softening in my chest. The scale of it, not the distance, though the distance is real and enormous and specific, but the human part of it. A person who spent his life looking up, grinding his own lenses, teaching himself to read the sky, who found a world at the edge of everything known. That person is now past the edge, going farther, not stopping. He earned it, I think. And the spacecraft carrying him is still working, still pointed at the sky, still collecting the glow of galaxies he never knew about, measuring a cosmological question he never imagined, with instruments that didn't exist until long after he was gone, doing science on behalf of everyone who has ever wondered what else is out there. That is the whole story in miniature. You build something, you send it somewhere, it does what you asked of it, and then it keeps going. And what it finds, long after you expected anything from it, changes the question you were asking. You thought you were measuring the dark, and the dark came back twice as bright.
And then you thought you'd explained it, and it turned out you'd explained most of it, and then other people looked again and said, not all of it, not yet. And the question is still open, and the spacecraft is still out there. And a man's ashes sail with it. Back at the start of this, I asked where you're listening from tonight.
Wherever that is, whatever room, whatever bed, whatever corner of the world is yours in this particular hour, the same sky is above you, the same darkness, the same photons passing through it, some of them the oldest light in the universe, traveling all this way to reach the thin atmosphere above your head. New Horizons is out there in that sky, too far away to see, too far away to communicate with in real time. A message sent to it right now would take more than 8 hours to arrive. The reply would take 8 hours to come back. By the time the exchange was complete, you'd have slept and woken and had breakfast, and the spacecraft would be a little further away. The darkness it sits in is the same darkness above you. You're just on different sides of it. And the question it's trying to answer, whether the universe is brighter than we think, whether there is more history, more structure, more ancient light than our catalogues can hold, that question is not separate from you. You are part of the census. The atoms in your body were forged in stars, in the nuclear burning that produced the very light being counted. When LORRI measures the cosmic optical background, it is, in some small and specific and entirely real way, measuring the glow of the same stellar generations that eventually produced you. You are in the data, not metaphorically, chemically. The carbon and oxygen and iron and calcium that make up your body were produced inside stars that contributed to the very background light being measured. Those stars burned, and they died, and their light went outward in all directions, and some of it went toward new horizons, and new horizons caught it. And you are here listening to this made of those same stars. The universe is large, the dark is real and enormous and mostly empty, but what fills the dark thinly and persistently from every direction is light. Old light. Light from things that burned for millions of years and then gave out. Light from things still burning right now. Light from galaxies so distant their stars will never have names. All of it crossing the void, all of it arriving somewhere, all of it carrying information about what the universe has been doing since the CMB went quiet and the first stars began to ignite. New Horizons is catching a little of that light. Right now, it will keep catching it until the plutonium fades and the power finally gives out, sometime in the late 2030s most likely, and then it will fall silent the way the Pioneers fell silent, the way the Voyager's cameras fell dark. It will keep moving. Nothing out there to slow it, no friction, no resistance, but it will stop talking. And what it has sent back, all those kilobits at a time, will be what we have. The team will still be analyzing it. The arguments about the residual excess will still be active. Whether the universe is too bright will still be a question, but the data from New Horizons will be in it, somewhere. In the papers, in the models, in whatever answer eventually emerges years or decades from now. A spacecraft built to see one thing that turned into a window onto everything. If you're still here, drifting somewhere between sleep and listening, that's fine. The ideas will still be here when you wake. The spacecraft will still be out there. The question will still be open. And somewhere aboard it, in a small container traveling at 13 kilometers per second through the cleanest dark any human instrument has ever known, an ounce and a half of ashes is sailing past the stars. Good night, wherever you are. If this slow journey through the dark was something you wanted more of, a like and a subscribe means more than you might think. Small creators like me really do rely on your support to keep these nights going. And if you have a moment, tell me where you're listening from and what time it is in your corner of the world. I love knowing you're out there. The Night Watch has the dark covered. You can let go now, and here is where the story gets honest with you. Because the 2024 chapter, the one where the dust correction came in and the excess shrank and some of the headlines called it solved, that chapter didn't stay closed. Independent teams working separately in 2024 and 2025 went back into the data. They applied their own calibrations, their own estimates of the diffuse galactic light, their own careful subtractions, and when they were done, there was still something left. Not the full factor of 2 from the original 2021 measurement, but a residual. A remainder that the catalogued galaxies, even after accounting for the scattered Milky Way glow, don't quite explain. How large is it? How confident are the teams? That is exactly the argument happening right now. In the journals, in the correspondence between researchers, in the next round of papers being written. It's not a fringe disagreement, it's a genuine, active, scientific dispute between careful people working from the same basic data and arriving at different answers. The measurement is hard, the foregrounds are hard to subtract, the calibrations are genuinely contested. So when you ask whether the universe is too bright, whether the cosmic optical background, the total sum of every galaxy that has ever shone, exceeds what our catalogues say it should, the honest answer in 2025 is, we don't know yet. The case is open. Not hyped open, not dramatically unresolved in a way that sells clicks, just genuinely, quietly, scientifically unresolved, which is, if you think about it, exactly what the edge of knowledge always looks like from the inside. And a 19-year-old spacecraft, 60 astronomical units from home, is one of the very few tools that can push the answer forward. Think about what that means for a moment, because it's a strange and rather wonderful thing. New Horizons was built to see Pluto. That was the whole point. The Long-Range Reconnaissance Imager, LORRI, was designed to resolve the surface features of a frozen world at the edge of the solar system, to see mountains and plains and the heart-shaped expanse of Tombaugh Regio from 12,000 kilometers away. It was a planetary camera, a close-up instrument for near targets as these things go. Nobody designed it to weigh the light of the universe. And yet here it is, pointing at empty patches of sky far from the galactic plane, collecting photons from sources billions of light-years away, measuring a background glow so faint it is measured in nanowatts per square meter per steradian. A unit of brightness so small it has essentially no equivalent in everyday experience. The camera was repurposed. The distance became the instrument. The fact that New Horizons ended up far enough from the Sun to escape the zodiacal dust, far enough from Earth to leave the airglow behind, far enough from everything to finally see a genuinely dark sky, that fact transformed a planetary probe into a cosmological observatory. The Voyagers are farther. Voyager 1 is past 160 astronomical units now, more than twice as distant, sailing deeper into interstellar space. But its cameras went dark decades ago. Power was always scarce on those spacecraft, and the imaging systems were the first to go. Pioneer 10 and Pioneer 11, the original trailblazers, went silent years ago. Pioneer 10's last detected signal came in 2003, Pioneer 11's in 1995. They are still out there, presumably moving without friction, without resistance, but they stopped talking and we have no way to listen even if they wanted to. New Horizons is the lone seeing eye. Of all the human objects sailing away from the Sun, beyond the planets, into the dark, it is the only one still carrying a working, sensitive optical camera. The only one still sending back pictures of the sky. Which means that if the question of the cosmic optical background is going to be answered by something we built, it is probably going to be answered, or at least meaningfully advanced, by this one spacecraft working with a declining power budget, a communication lag of more than 8 hours each way, and a data rate measured in kilobits per second. The extended mission has been approved. The science continues into the late 2020s. The radioisotope thermoelectric generator, running on the slow decay of plutonium-238, is expected to keep producing enough power into the late 2030s if it is managed carefully, if the team keeps making the hard choices about which instruments to run and when. There may even be one more close encounter if the searches pay off. The Subaru telescope has been used to scan for Kuiper Belt objects within reach of New Horizons' remaining fuel. No confirmed target yet, as of the mid-2020s. No guarantee there will be one. But the search continues, and the solar system has a way of holding surprises. Even without a flyby, the spacecraft has work to do. The heliosphere's outer edges, where the Sun's influence fades and interstellar space begins, are poorly mapped. The dust streaming in from beyond the solar system, the charged particles, the faint structure of the boundary itself. New Horizons sits in the middle of it, measuring the way a ship at sea might take soundings of an unmapped ocean floor. But it is the dark sky measurements that carry the deepest question. And the deepest question is this: if the residual excess is real, if independent teams keep finding it after the best dust corrections anyone can do, then where is that extra light coming from? The mainstream explanation, the one that doesn't require new physics, is actually quite profound in its own right. It would mean that our surveys of the universe, even the Hubble ultra-deep field, those extraordinary long exposures of tiny patches of sky that revealed thousands of galaxies in what looked like empty space are still missing something. A population of galaxies too faint or too diffuse to count individually, but whose collective light adds up. The universe would contain more stars, more history, more of everything than our best catalogues have recorded. We would have undercounted. And the audit, the cosmic optical background measured by a planetary camera 60 AU from the Sun, would be telling us so. The other explanation, the minority view, the long shot taken seriously precisely because the data is genuinely contested, involves new physics, particles decaying into photons, something in the dark producing light that shouldn't be there. It remains on the table, not because it's likely, but because the question isn't settled enough to take it off. And while that argument continues, the light that LORRI captured keeps traveling. From New Horizons to Earth at the speed of radio waves, taking more than 8 hours to arrive. Then through the processing, the calibration, the subtraction, the debate. Then into the Astrophysical Journal where Todd Lauer's original paper landed in 2021, where Mark Postman's refined analysis followed. Then into the next paper, and the one after that, and whatever synthesis eventually emerges years from now, when someone finally draws the line and says, here is what we know. Right now, you are made of the same light being measured. The atoms in your body were forged in stars. The stars shone. The photons they released spread outward in all directions, and some of them were lost, and some of them hit planets, and some of them were absorbed by gas clouds, and some of them, the ones that escaped all of that made it out through billions of years of expanding space, are part of the cosmic optical background, the universe's total output, the audit of all the burning. At 60 astronomical units, sunlight is about 3,600 times fainter than it is here. If you stood there in the space between New Horizons and the next star, you could cover the sun with a pinhead held at arm's length. The sky in every direction would be stars. Faint, unhurried, ancient. The glow of galaxies too distant to resolve, too numerous to count, blending into something that is almost darkness, but isn't quite. And somewhere in that almost darkness, something is brighter than it should be. Clyde Tombaugh spent his life looking up. He was 24 years old, working at the Lowell Observatory in Flagstaff, Arizona, when he found Pluto in 1930, comparing photographic plates taken days apart, looking for the tiny shift that would mark a moving object against the fixed stars. He found it. He spent decades more mapping the sky, searching, teaching, accumulating the patient hours of someone who genuinely loved the work. He died in 1997, 8 years before his planet was demoted, 9 years before the spacecraft named after an explorer carried his ashes off the launch pad. A small portion of his remains is aboard New Horizons in a container on the spacecraft. The inscription reads, "Interned herein are remains of American Clyde W. Tombaugh, discoverer of Pluto and the solar system's third zone. He flew past Pluto on July 14, 2015, closer than any human-made object had ever come. 12,500 kilometers above the nitrogen ice plains he'd been the first to know existed, above the heart-shaped expanse that bears his name. And then he kept going. He is going now. At 13 kilometers per second, outward into the Kuiper Belt and beyond, into the dark that LORRI is measuring, into the space where the zodiacal dust thins to nothing and the sky finally shows its true color. Clyde Tombaugh sailed past Pluto. And he is still sailing. That is what a life spent looking at the sky earns you, if the timing is right, and the people who loved your work decide to honor it that way. Not burial, not stillness, perpetual motion through the cleanest dark any human instrument has ever known, in company with a camera that is measuring the total light of everything that has ever burned. So, where are you listening from tonight? That was the question at the start of this. Still the right question now. Because you are somewhere, in a room, on a train, in a bed with the lamp still on or already off. And the universe is the same one that New Horizons is measuring from the outside. The cosmic optical background includes light that passed through or near wherever you are on its way across billions of years of space. You are inside the audit, not outside it. The spacecraft is 8.9 billion kilometers from home, and home is wherever you are. If this slow walk through the dark was good company, through the anomaly, the dust correction, the reopening, the honest uncertainty still sitting in the journals waiting for more data. A gentle like and a subscribe helps more than you might expect. Small creators like me rely on that support to keep these nights going. And if you want to leave a word, tell me where you're listening from and what time it is where you are. I read everyone. The Night Watch has the dark covered. You can let go now.